So our next speaker is Garbe. So Louis completed his PhD at University Diderot in Paris, supervised by Angela Keller and co-supervised by Simone Felicetti, whom we know very well. And then he moved for a postdoc at Technical University of Vienna to work with Diderot. And when he moved to Garbe, he also moved with him. And he's currently here as a postdoc at one of the Master Institutes. So Louis is an expert in quantum optics, also quantum metrology, quantum sensing.
In another life, yeah.
In another life. We show us most of our interest here in this group. So please.
Thank you very much, Francesco, for having me. So first of all, I would like to apologize that my co-Italian won't allow me to greet you properly like Sasha did, but I would like to thank all of you for coming here despite the post-lunch slumber. Since it's 2:30, actually already 3, I thought it could be useful to make a little routine before we start. So if you want to imitate me, please put your hands in front of you like this. Yes. Then turn them, push them as far as possible when you leave them. That helps wake you up a little bit, which is always useful when you have a talk at this time. Okay, so today I'm going to talk about the work I've been doing during my postdocs in Vienna and Munich. I will talk about a range of different topics, so please interrupt me at any time. I don't know whether I come to the end, but what is really important, I think, is that we have some discussion about these topics. Let's say broadly, I'm going to talk about the use of reservoir engineering to realize many-body physics in photonic system. Or to put it in a slightly more sexy way, I will tell you why you should care about the environment. Okay, as a warm-up, let us start by defining what I mean by many-body physics with photons. So if we think about atomic particles, we are talking about, in principle, massive interacting particles. So if we take, for instance, a system of atoms in a box, a very important property that they are is that through their interaction, either short or long range, they can redistribute energy, they can exchange energy, so you can redistribute energy between different modes without losing particles. And one consequence of that is that you can get then a thermalized cloud of atoms, for which with temperature is a priori independent of the number of atoms you have in your cloud. So the issue is with with photons. If you try to do the same thing with photons, you run into a range of problems, but two of them in particular. First of all, I was talking about interacting particles, but photons don't interact. Well, that's actually not true. Photons do interact, in particular through this box-like process, but this is relevant for energy. You can see it here, but for energy, basically, of the order of mega electron volt, or if you prefer, picometer wavelength. And since we don't know yet how to do quantum optics with gamma rays, it's not what I'm going to talk about. So for all practical purposes, photons don't interact. First difference with atoms. Second point, I was talking about thermalization. Just want to remove it. Okay, I was talking about thermalization. Well, there is a way to prepare a thermal bath with photons, and that's just black body radiation. The problem is, if you take a cavity and you hit the walls, well, at some point you will start emitting photons and there will be in a thermal state. The issue is, in this case, the number of photons you have depends on the temperature. So if you change the temperature of your system, you will also change the intensity of your light. And one consequence of that, which is, so one thing you can do with these atoms you cannot do simply with these photons, is Bose-Einstein condensation. If you take your set of bosonic atoms and you cool it down while keeping the number constant, at some point you will observe Bose-Einstein condensation where all particles, or macroscopic fraction of them, accumulate in the same ground state. If you try to do the same with your black body radiation, if you try cooling down your system, you're just going to stop emitting photons. So at low temperature, you're not going to get a BEC, you're going to get just nothing. Yeah? So let's keep going. So as I was mentioning, the So those are some of the differences that we have between photons and usual, let's say, interacting massive particles. And one of the difficulties that you encounter when you try to do many-body physics with photons. So what in this talk, what I'm going to tell you about is essentially, can we go beyond this simple paradigm of gain and loss? Can we make a photonic system interact with its environments in a different way through a control process, which then will allow us to steer a system towards a state we're interested in. So the name of the game is to do reservoir engineering to generate photonic many-body states, and in general also many states with other bosons. So to be a bit more specific about the kind of process I have studied, it's about environment-assisted transfer. So to explain this, I'd like to take the example of this experiment that was done at the institute in Munich where I work by the group of Kirill Fedorov. So basically, those are superconducting circuits, but the same idea could be applied also to whole atoms of optical photons. The idea is quite general. And what they are interested, so they are superconducting circuits that can hold microwave photons. Now, what they want to do basically is to make a detector, microwave photodetector. So their setup looks like this. You have here this horseshoe resonator, which basically hosts different bosonic modes, which colored here the so-called waste mode and buffer mode. And you connect this resonator to a superconducting qubit here. And the idea is that photons are going to be coming on this buffer mode, and we would like to transfer them over and to store them in these qubits. And then they are very well established technique to read superconducting qubits, so you can detect whether it has been excited or not. But the catch is you want this transfer to be irreversible, because if your photons is allowed to get to a qubit and then back to the buffer mode or some other modes, of course this is going to affect your reading fidelity. So to achieve this, the way they do it is through a coupling to this extra mode, which is called the waste mode. So it works as follows. First of all, you have a photon which comes on the buffer mode and excites it. Then you have this free-body interaction, which basically destroys an excitation in the buffer mode, while creating simultaneously one in the qubit and in the waste mode. And the waste mode is called like this because it's extremely dissipative. So it's going to very quickly lose the excitation it just gained. And the next process then will be just a transfer of one excitation from the buffer to the qubit. Another importantly, if the excitation wants to hop back, it has, through the reverse process, it has to absorb energy or to absorb one excitation from the waste mode. But as I just said, the waste mode is now empty because it just loses its excitation. So that means that this back-hopping process is suppressed. And so we obtain an incoherent, irreversible transfer between two bosonic modes. And you can then generalize this a little bit more. And if you say that your waste mode doesn't just lose particle, but is in a thermal bath, so then it can absorb and made it, you will find in general that what you get is an incoherent transport process with forward and backward rates, whose ratio depends on the properties of its waste mode, basically its frequency and its temperature. And then by tuning the temperature, so for very high temperature, you will have essentially equal hopping forward and backward. For zero temperature, you will have unidirectional hopping. So this is the kind of process that they used in this experiment to transfer these excitations to qubits. And what we study is basically a many-body or multi-mode version of this. So now instead of just one buffer, one qubit, what if we have now a series of modes? For instance, those could be separate LC oscillators, or I gave an example later in a superconducting waveguide. But now we have not just two, but a series of multiple bosonic modes, and we can have particles hopping between them incoherently through this kind of process. So this kind of process, which I'm going to describe in a minute, is what most of what I've been working on, and what I'm going to talk about now. So if you come back to my original description, original shortened list
of what we want to do for many body physics with photons, I said that we wanted to have some energy, some process that allows you to redistribute energy without losing particles. So this is what we have here. And we want to have something which a priori gives us a thermal distribution with independent temperature and particle number. But I still haven't talked about interaction. For the moment, our particles are still non-interactive, or at least not interacting directly with one another. But to that I would answer, so what? Actually, as it turns out, we can have many body physics even without direct interaction between photons. So to explain this, let me have a closer look at this incoherent process that I mentioned just a second ago. And let's look at how particles behave when they evolve according to this popping process. So if we have, let's say, classical particles in the sense of particles that are neither bosons nor fermions, if you look at the probability that a jump will take place between two neighboring sites, two neighboring modes, is just proportional to the number of population of the number of excitation in the original mode. Each particle has the same probability to jump. So the total probability that one of them will jump is just proportional to n. Now, if instead you have bosons, what you find is that the probability depends not just of the population in the original mode, but also of the number of bosons in the target mode. It's a sort of effect similar to the stimulated emission. If you are emitting into a mode which is already occupied, your emission probability is amplified. So that means that even in this case where we have no direct interaction with our bosons and no coherence, we still have a signature of the bosonic statistic that survives. That gives rise to something we can call stimulated transports, for want of a better name. And as a side note, we can also play the same game with fermions with the exact same model. And in this case, we find that we get the same popping probability but with a minus, meaning that if the site in front of you is already occupied, so if n equals 1, this probability falls to 0. So you cannot jump to a site which is already occupied. And as it turns out, this model here with fermions is quite famous in statistical physics. It's called an exclusion process, or AZEP, and it's been used extensively in statistical physics to describe, well, fermionic systems, but also, for instance, equations like traffic jams, and more generally, when you have 1D transport where you have an exclusion process that forbids two particles to sit at the same place. And what we studied is sort of the mirror image of it. If you have bosons instead of fermions, you get something that we very imaginatively call the AZIP inclusion process, in which the jumps to a site already occupied are amplified instead of being suppressed. Now, to give you a bit of an idea of, okay, you may ask, okay, why should I care? Why is it interesting to look at this bosonic problem? Just to give you a flavor of the kind of fun stuff you can observe in these processes, one of the first things we tried with this model was to plug it, to drive it out of equilibrium. So essentially, we plug reservoirs in both ends. We inject particles here, we let them pop, and we extract them here, and we just look at the kind of dynamics and steady state we can get. And we find that we can observe some very wonky phases. So for instance, this staggering density phase. So here again, I'm repeating here, we're in a situation where you just inject particles here, you let them move in one direction. In this case, it was even in a totally asymmetric case, so they can move only one way, they never go back. They are extracted here, so there's no back reflection, nothing at all. They are not interacting, and yet, because purely due to this statistical effect, they are sort of aware of each other's presence and can lead to this complex density phase. And the one way, one way to see it, but one analogy that I like to take is actually about, again, this traffic jam. You know that if you have cars on the highway, they always go in one direction, they never go back, at least they're not supposed to. I don't know how it works in Palermo. And yet, because you have, in this case, this exclusion process, if you put a choke point on your road, so if some of them starts slowing down, you can see the form of this density wave, or this accordion wave that forms and propagates in the direction opposite to the way they move. So here you have a similar effect where particles move only one way, but because of this inclusion process, you can see the formation of the structure that develops in the direction opposite to the transport. Maybe to give you tiny bits of intuition about where this weird zigzag come from. If you look at the equation of motion describing your system, you can find that you have a term that describes your current, and the term which is really important in it is this one, which is basically encode this non-linearity. And if you focus on this thing and you think about what it means, you see that if you have, let's say, a configuration where you have just an exponential, so where you have, let's say, n1 is bigger than n2, is bigger than n3, then the product here, n1 and 2, is always bigger than n2 and 3. So that means that the population escaping from 2 to 1 is always bigger than the population incoming from 3 to 2. And as a consequence, that means that this site loses particle, so this configuration cannot be stable. You can play the same game with, for instance, an armchair or any kind of configuration, and at the end of the day, you find that the only thing that can be stabilized under this kind of non-linear transport process is this kind of zigzag, because here you see that if n1 equal n3, then automatically n1 and 2 equal n2 and 3. So this kind of configuration can be stable under the non-linear process. What we have in general then is a competition between this non-linearity and some standard diffusion. Okay, I would like to go off on a tangent for a second. But first of all, I would like to ask whether there are any questions, comments, or insults on the topic.
Maybe just an observation.
An insult?
This kind of process that you have two planes.
Yep.
They do depend a lot on the magnitude of the open rate, or they just enhance? Or
What do you mean by depend on the...
Like if you have like the chirality is very dependent on like having one much bigger than the other open rate, and the difference between the two.
So you mean you ask whether observing these effects depends a lot on the...
Yeah. So as the answer is not too much. Okay, there are two things. First, you can compare what happens if you have some asymmetry compared to no asymmetry, and there you find that basically any amount of asymmetry, or any amount scaling that 1 over the system size will give you a completely different profile. So the impact of this, this non-linearity that comes from bosonic enhancement, basically it's revealed as soon as you have even a little bit of asymmetry. So this thing is really quite typical. Then specifically to observe this zigzag and this kind of process, you need to crank up the asymmetry a little bit more, but it doesn't need to be insane either. But however, I would argue that this guy over here, as soon as this thing, so you see this guy over here is really zero if you have the asymmetry, because the effect kind of cancels out in case, but as soon as this thing is a little bit non-zero, so more specifically bigger than 1 over the system size, you immediately see a big difference.
Also, just another question about this picture that you're written here. Can you see? Can you interpret this like as some sort of Markov chain? Because this is literally a process going back and forth. You can run this as is, and you can calculate its stable using the
Markov chain. I never thought about it in terms of Markov chain. What I can tell you is that at some point I did calculate the exact steady state. So this profile here, I could calculate it exactly. And the way I did this was through a recursion relation. So basically, thanks to some shenanigans, I could compute the population here. And then in the steady state, I have a recursion relation that allowed me from this state to calculate this one, then this one, then this one, then this one. So in this case, I guess it's similar to a Markov chain, in the sense that knowing the population at one side, you can calculate the one of the next But I never thought about it like this.
Yeah, I mean, I think it's easy to write the matrix of the matrix and just check it.
Yeah, okay, yeah, no, yeah, I mean, I will be happy to discuss this. I never thought about this like this. Okay, more questions? Yeah, so I wanted to get off on a tangent for a second and just to tell you about the way that I started thinking about those processes recently, which is about from the perspective of gauge field, from stochastic gauge field. So if we take the time binding model that we all know and love, in general, what it describes are particles hopping on the lattice through the interaction of a gauge field, and the effect of this field is basically to add a phase to the forward and backward hopping process. And you can, of course, then generalize this to 2D or more dimensional process. And in the simple way, for instance, of electrons in the metal, this could be obtained by applying a magnetic field, and then this phase is just a Pyre's phase of the integral of the magnetic potential. Now, in this picture, what is important is that this phi here is just a number, just a scalar. So basically, what you assume is that the field is both constant and not fluctuating. It's a purely classical field without dynamics of its own. My question now is, okay, but now if you start preparing your system concretely, and if you also want to start preparing like a simulated, for example, a quantum simulator with an effective magnetic field, for instance, using laser in atomic optical lattice or in superconducting circuits, then this gauge field in general is going to be implemented by an ancillary system, which can itself be coupled to the environment. So it can now have its own dynamics, it can be noisy, it can be driven dissipative. So the question is, in general, what happens if we start taking it to adding a bit of shit, if you want, to this gauge field? And maybe just to take one of the simplest example I can think of. So it's an example I take from this paper, but there are many others that consider the same ideas. So if you take two resonators, which you couple to a collective mode, which you couple together to a dissipative mode, you can generate collective dissipation in this superposition. So now if you look at the dynamics of the amplitude of each mode, they will take this form. So you have here the gamma that comes from the collective dissipation and the J that comes from the usual ordinary form. What is important is that if you tune your parameter to this regime, you can see easily that this term here will cancel out, but this one here won't. So that means essentially that you see that the system alpha 1 still influences the amplitude of the second site, but not vice versa. So what you are doing, so through this collective dissipation, you are engineering a non-reciprocity in your system without having to resort to magnetic field or things like this. So here you break time reversal symmetry through dissipation instead of vector field. And one way another way to look at this is to say that in this time binding model, now you've elevated the phase in your system to be not just a real but a complex number, meaning that you will have an amplitude for this two hopping process that will not be different. And that means that your Hamiltonian partially becomes non-dimensional, which is all the rage right now. So that's one first way, let's say, of generalizing this normal gauge field. Now, so far I've used this driven dissipative aspect of the field, but I haven't talked really about what happens if the field is noisy. So what happens now if it's not? What happens now if this field is stochastic, just a scalar as before, real complex? We now have an object which is a linear process, for instance. So that means that the stochastic quantity, which on average is zero, but whose variance is non-zero. And as it turns out, this kind of stochastic Hamiltonian can be studied properly by looking at the density matrix and can be described as the Midland Maxwell equation. And lo and behold, the Maxwell equation describing this kind of system is precisely the kind of AZ model that I was talking about before. So this is a point that I am, as I say, it's a way of thinking that I only recently started to consider, so I haven't explored all the consequences yet. But I think that these processes, this kind of weird number conserving non-reciprocal processes could be an interesting way of generalizing the type binding model in a way slightly different than the usual non-animation and Newtonian. As I said, still very much work in progress. So if you have any idea or input about this, I would be delighted to listen. Okay, tangent over. Now, in the very few minutes, but in the -2 minutes that we have left, I'm just going to flash super quickly the latest result that we got with Lucas, a PhD in your group, which hopefully should come up this week. And it's coming back to what I said at the very beginning, using now an engineered environment to generate a thermal state with photons with a temperature independent of the particle number, and in particular to use this process to generate a Bose-Einstein condensate with photons. So actually this has been done in the optical regime, but what we wanted to see is it possible now in our superconducting circuits to refrigerate a bath of microwave photons and to produce a BEC with microwave photons. So in a nutshell, the idea is that we're using a multimode resonator, just a waveguide, which we couple to dissipative elements in order to engineer this transfer process. So this time we don't have a chain, we don't have separate resonator, but we have different modes, energy levels in a single resonator, and we are transferring over particles between the run of this ladder. And the idea is that we want to use an effectively low temperature process to force particles down this ladder and make them accumulate into one state. And yeah, we will also skip all the details, but basically the point is that if we let our system thermalize at the temperature of our fridge, we should obtain a certain temperature, which is what typically 10 microkelvin. But by adding on top of this engineered bath, we see that we can force particles to leave. So those are the oscillation of each of the energy modes. We can force particles to leave this intermediate mode and to accumulate into one state. So we can show that we effectively thermalize a system at a temperature which can be effectively an order of magnitude or lower than the fridge temperature. And by accumulating particles into one state, make them produce actually a Bose-Einstein condensate. So as I say, these results should be hopefully out at the end of before the week is out. So to wrap up, I showed you how we can essentially, by using the reservoir engineering technique, go beyond the simple setup of Gaussian loss for photons and other bosons, and implement some number conserving process, at least to some interesting many-body transport dynamics. I discussed very briefly how we could use this to actually achieve cooling and condensation in microwave platform, and maybe this outlook or this way of thinking about this as a generalization of these gauge field processes, which could be interesting for the future. So with that, let me thank my collaborators, mostly Lucas and my boss Peter, and previous collaborators from Vienna, and I'd be happy to answer the other questions if you have.
I have a question for this fantastic type binding model. Is that somehow related to like bond disorders, like stuff, during all lattices? Yeah. I mean, like you have some strength of jump between the sides, and then you have many snapshots to collect some averages and so on.
So you mean more in the direction of like Anderson localization? And
Yeah.
I think it's a bit it's slightly different in the sense that here it's here, but a bit different in the sense that here it's not that. As far as I understand, in the case that you described, the rocking rate is fixed everywhere. It's just that it's different from one to the other. Here it's more that the rocking rate fluctuates in time in front of each other. And in particular, that means that you don't have things that understand localization or anything. And actually, it's even the other way around, because in that time we talk about this, you can there are things that suggest that if you start from a system which is localized, or some and you add a little bit of stochastic forming process that can actually help you to overcome the localization and restore transpose.
Questions?
So maybe
Yeah.
so I didn't understand the connection. Can you repeat about the connection between this fluctuating gauge field and the Lorentzian physics?
I don't know if there is a connection, but the point that my at least, as I said, still very naive and developing approach is more or less, in general, we start from this Taiwanese model and we try to understand how we can generalize these objects, so it's space. So one first way of generalization is to say, okay, it's still constant, it's still scalar, but now it's complex. And my point is, the next generalization is, what if this thing actually has a time dependence, or is allowed to fluctuate in time? And in the simplest thing I think we can think about is that if this phi then is a completely stochastic process, then that's a kind of stochastic Hamiltonian you get, and the kind of process you get. So it's, let's say, in the direction of as soon as this gauge field is not just a constant scalar classical object, as soon as it starts having some familiar property, what kind of model can you get from them? So it's this direction of, this is a different way of generalizing the Taiwanese model. Yeah.
Does the kind of noise matter, the correlator? Like, is it a white noise or cobalt noise?
You mean here? I mean, okay, so are there no correlation basically between these two processes? Yeah, okay, so I didn't say this. If you have two noises that are correlated, you will get really this master equation with distinct jump operators. If you have now the same noise, for instance, both or psi1 here and psi1 star here, you will, in this case, get a single jump operator, which is the sum of these two, which depending on the system we have, may or may not give you different dynamics. So I put that a little bit under the rug. But yeah, it's maybe even more intuitive to say that this thing is a complex conjugate of this thing, but it will still give you a similar process. Just, and provided you also have dephasing, the two should be equivalent, but not always. Yeah.
I wonder, in one key you get this standard patterns, so
Yeah.
is there no answer in 2D?
As some risk. That's what we're working on at the moment. So, and it's difficult. It's complicated. You know, but yeah, that's what we're trying to do at the moment.
Well, another question related to 2D generalization.
Yeah.
In 2D, you can have fermions, not just fermions and also baronions.
We say no onions. No idea. It's a fun thing to think about. But I've
That's the anionic traffic jam.
That would be amazing. Let's write a years here about that.
Okay, any more questions? If not, let's start to read and touch again for